Nuclear energy is a form of energy released from the atomic nucleus, and in this video we will study two means of obtaining energy from nuclear reactions. Fission, in which a large nucleus splits into two smaller nuclei, and fission, in which two small nuclei fuse to form a larger one. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. Let's start by reminding you what the binding energy is. Binding energy is the amount of energy released when a nucleus is formed. The total mass of a nucleus is less than the total mass of the nucleons that make up the nucleus. And using the mass-energy relation, we can see that this mass difference becomes the binding energy of the nucleus. Consequently, the higher the binding energy, the more stable the nucleus, and the greater the binding energy, the less the total mass of a bound system. The following graph shows the binding energy per nucleon as a function of the mass number. Iron has a mass number of 56, and is one of the most stable of all the elements. We say that iron has a high binding energy per nucleon. So the binding energy per nucleon is a good indication of nuclear stability. The graph has a flat intermediate region extending between A equals 30 and A equals 170. In this region, the binding energy per nucleon is almost constant, and they are stable. When the mass number is less than 30, we have the region of lighter nuclei, and the very light nuclei have low binding energies. So, very light nuclei can combine to form heavier atoms with larger binding energy. Therefore, tend to be more stable. When the mass number is greater than 170, we have the region of very heavy nuclei, and very heavy nuclei have low binding energies. Thus, very heavy nuclei can form lighter nuclei with higher binding energies, and which are more stable. When a heavy nucleus splits, we call fission. When two light nuclei come together, we call fusion. Let us now study nuclear fission in more detail. When a nucleus undergoes alpha or beta decay, the number of protons or neutrons of the daughter nucleus is a different element from the parent nucleus. This transformation of one element into another is called nuclear transmutation. The other way for a nuclear transmutation to occur is through nuclear reactions. When a nucleus is struck by another nucleus, or by a simpler particle such as a gamma ray, neutron, or proton, the resulting interaction is referred to as a nuclear reaction. We can symbolically write a nuclear reaction as follows, where particle A is a moving projectile particle, or small nucleus, that strikes nucleus X, producing nucleus Y and particle B. We will now consider the energy involved in these nuclear reactions because energy must be conserved. In the video about radioactive decay, the disintegration energy of a radioactive decay was defined as the rest energy transformed into kinetic energy as a result of the decay process. Likewise, we define the reaction energy associated with a nuclear reaction as the difference between the initial and final rest energies resulting from the reaction. Because energy is conserved, Q has to be equal to the change in kinetic energy, final minus initial. Let's solve an example to make the theory clearer. We take the formula to calculate the reaction energy and substitute the values given the problem. Now let's study a particular type of nuclear reaction, nuclear fission. Nuclear fission occurs when a slow-moving neutron strikes an unstable very large nucleus, such as uranium or plutonium. Being uncharged, the neutron is not repelled by the nucleus. The absorption of the neutron creates a nucleus that is unstable and can change to a lower energy configuration by splitting into two smaller nuclei. The fission of 235 uranium can be represented by the reaction, where 236 uranium is an intermediate excited state that lasts for approximately 10 to the power of minus 12 seconds before splitting into medium mass nuclei X and Y, which are called fission fragments. In any fission reaction, there are many combinations of X and Y that satisfy the requirements of conservation of energy and charge. In the case of uranium, for example, approximately 90 daughter nuclei can be formed. Let's solve one example. We take the formula to calculate the reaction energy and substitute the values given in the problem. Since the fission fragments are more tightly bound, the sum of their masses is less than the mass of the uranium, and the total energy released per fission is 200 mega electron volts. This is an enormous amount of energy for one single nuclear event. At a practical level, the energy from one fission is tiny, but if many such fissions could occur quickly, an enormous amount of energy at the macroscopic level would be available. This occurs when we have a chain reaction. An atom of uranium-235 undergoes fission by bombarding it with neutrons. Along with barium and krypton, 3 neutrons are released during the fission process. These neutrons can go on to be absorbed by other nuclei if they are slowed down by a moderator, a medium such as graphite, heavy water, and beryllium that causes the neutrons to travel more slowly. If these neutrons are absorbed by other nuclei, it makes a chain reaction. For the chain reaction to occur, there has to be a critical mass, and you might be wondering why. Because a neutron ejected by a fission event travels certain average distance through the material before it encounters another uranium nucleus and triggers another fission event. Without sufficient mass, a neutron is likely to escape from the sample before finding another nucleus. In a bigger piece, a neutron can move farther through the material before reaching the surface. For 235 uranium, the critical mass is about 15 kilograms. Uranium has a very high density. This mass is equivalent to the size of a tennis ball. Look at the next example. For 235 uranium, 1 mole of this isotope has a mass of 235 grams. To find the number of nuclei in our sample, we use Avogadro's number as follows. We now multiply the number of nuclei in our sample by the energy yield per nucleus, obtaining the total disintegration energy. We can see The energy contained in 1 kilogram of uranium is very large. The table below compares the energy that 10 grams of uranium can release compared to other energy sources. Let us now study what happens in the process of nuclear fission. Very light nuclei can combine to form heavier atoms in a process known as nuclear fission. Because the mass of the final nucleus is less than the sum of the masses of the original nuclei, there is a loss of mass, accompanied by a release of energy. Look at this example. We take the fraction energy and substitute the values given in the problem. This energy is carried off by the deuterium and the gamma ray. All stars generate their energy through fusion processes. The energy produced by fusion increases the pressure inside the star and prevents its collapse due to gravity. The binding energy per nucleon increases as we go from hydrogen to helium. It means that helium is more stable than hydrogen, and the energy output of our Sun is due mainly to the following sequence of fusion reactions. Let us now compare the energy released in fusion with that released in fission. We take the formula to calculate given in the problem. Note that the energy released per nucleon in this reaction is nearly 2 times the energy released per nucleon in a nuclear fission process presents itself as a more viable energy option. However, the process of fission is more difficult to achieve than nuclear fission because the deuterium and hydrogen are positively charged. The range of the nuclear force is short, hardly beyond the nuclear surface, but the range of the repulsive Coulomb force is long, and the force thus forms an energy barrier. Let's see how it works with the next example. The mechanical energy of the system is conserved. So the initial mechanical energy is equal to the final mechanical energy when they stop. The initial energy consists only of the total kinetic energy 2 times k of the 2 nuclei. When the nuclei stop, the energy consists only of the electric potential energy of the system. If we treat the proton gas as an ideal gas, then the average kinetic energy is related to Kelvin temperature as follows, where K is the Boltzmann constant. More careful calculations show that the temperature required for fusion is actually about an order of magnitude less than this rough estimate, partly because it is not necessary that the average kinetic energy be 0.22 megaelectronvolts. A small percentage of nuclei with this energy would be sufficient. 2 conditions must be met before nuclear fusion can occur. First, the nuclei must be highly energetic to overcome the repulsion force. This means high temperatures. Second, The density of nuclei must be high enough to ensure a high rate of collision. Nuclear fission isn't used yet for energy production because it currently requires more energy to initiate the reaction than it produces, and it is hard to find materials that can withstand such high temperatures.